November 9th, 1676. A Danish astronomer named Ole Rømer stands before the assembled members of the French Academy of Sciences in Paris and makes a prediction that almost everyone in the room believes is wrong. He says that an eclipse of Io, one of Jupiter's moons, will arrive 10 minutes late, not approximately, not sometime around then, 10 minutes to the minute. The other astronomers are skeptical. Io's eclipses had been measured and catalogued for decades. The tables were established. The timing was known. A 10-minute deviation was not a small discrepancy. It was an accusation against the accumulated work of an entire generation of observers. The night came, they watched, they waited. The eclipse arrived 10 minutes late, exactly as Rømer had said. He had not predicted a flaw in Io's orbit. He had measured something no human being had ever measured before, the speed of light. The eclipse was late because the light carrying its image had to cross an additional distance, the extra space that had opened between Jupiter and Earth since the previous measurement. Light was not instantaneous. It traveled, it took time. What the Academy understood that night was that Rømer had made a remarkable calculation. What no one understood, not Rømer, not the Academy, not anyone in that room, was the consequence buried inside that calculation. A consequence so large that fully absorbing it requires sitting with it, quietly over a long period of time. There is a name for what that consequence becomes at cosmic scale. I will come back to it. For now, understand only this. If light takes time to travel, then everything you have ever seen without exception is already in the past. Look at your hand. The light that enters your eye when you look at your hand left the surface of your skin approximately 1 nanosecond ago. 1 billionth of a second. The delay is real. It is also completely undetectable to anything you are equipped to sense. You have never seen your own hand as it currently is. You have seen a 1 nanosecond old version of it continuously your entire life and experienced it as the present. Now look at the sun. If it is day where you are, the light you are seeing left the solar surface 8 minutes and 20 seconds ago. If the sun were to disappear at this exact moment, simply cease to exist instantaneously, you would not know for 8 minutes. The sky would remain bright, your shadow would persist, the warmth on your face would continue. For 8 minutes, you would be living inside the afterimage of something that no longer existed. This is not a thought experiment. This is the precise physical description of how observation works. The sun you see is 8 minutes old. The image is real. The source may not be exactly as you picture it. Now extend the interval. The nearest star beyond our sun is Proxima Centauri, 4.2 light years away. The light arriving from it tonight left its source 4 years ago. Whatever Proxima Centauri is doing at this moment, whether it is unchanged or flaring or in some process of transformation, you will not know for 4 years. The star in your sky is a 4-year-old document. It is accurate. It is also ancient. The Andromeda galaxy is 2.5 million light years from Earth. When you look at it, you are seeing it as it was before our species existed, before Homo sapiens had walked any grassland, before the last common ancestor of humans had been born. The galaxy in your image is not a contemporary object. It is a 2.5 million year old artifact, delivered to your eye at the speed of light, arriving right now. The further out you look, the further back you go. This is not a limitation of instruments. It is not a problem that better technology will eventually solve. It is a constraint inscribed into the structure of reality by the finite speed at which information can travel. The universe, as you perceive it, is not the universe as it is. It is the universe as it was at various distances, at various points in the past, all arriving at your position simultaneously, creating the seamless illusion of a coherent present moment. That moment has never existed. What you experience as now is a collage assembled from light that left its sources at wildly different times in history. When you look at the night sky, you are not an observer. You are an archaeologist, sifting through layers of elapsed time, reading what was left behind. In 1908, a woman named Henrietta Swan Leavitt was working at the Harvard College Observatory for 25 cents an hour. Her title was Computer, not in the modern sense a human calculator employed to examine photographic plates and perform measurements that the male astronomers who directed the observatory considered too tedious to do themselves. The women in this role were occasionally referred to without kindness as Pickering's harem, after Edward Pickering, the director who hired them. Leavitt was assigned to the small Magellanic Cloud, a satellite galaxy visible from the southern hemisphere. She was searching for variable stars, stars whose brightness changes in regular cycles, and recording their periods and luminosities on paper. She found them, and then she noticed something that had no right to be there. The brighter a coveted variable star appeared at its peak, the longer its period of pulsation. Not roughly, not approximately, precisely. The relationship held across every star she measured, and she measured hundreds. The pattern was too consistent to be coincidence. It was a law written into the physics of how a particular class of star behaves. And what that law meant when you understood it fully was this: you could calculate how far away a star was. Not estimate, calculate. If you knew how long a Cepheid period was, you knew how intrinsically bright it was. If you knew how intrinsically bright it was, and you measured how bright it appeared, the difference told you its distance with precision that no previous method could approach. Before Leavitt, astronomers could not reliably measure the distances to anything beyond a few hundred light years. The universe, as far as any instrument could determine, was the Milky Way. Everything beyond it was argument and speculation. Her work ended that uncertainty. Within years of her discovery, Edwin Hubble used her method to measure the distance to Andromeda and determine conclusively that it was not a nebula inside the Milky Way. It was a separate galaxy, 2.5 million light-years away. The universe was not the Milky Way. The Milky Way was one galaxy among an incomprehensible number, each containing hundreds of billions of stars, each separated from the others by distances that reduced even the nearest to a faint smear on a photographic plate. What Leavitt's discovery made possible was a reckoning. The more precisely you could measure distance, the more precisely you could calculate how far back in time you were looking. The universe that astronomy now revealed was not a collection of objects. It was a collection of moments, a vast, three-dimensional archive of elapsed time, organized by distance, readable only in one direction, backward. Henrietta Swan Leavitt died in 1921. She was nominated for the Nobel Prize by a Swedish mathematician who had not yet learned she was dead. 4 years had passed. The nomination arrived at the Academy. The Academy replied with the information it had. The universe she helped us see had been transmitting its history to Earth for billions of years. She gave us the means to date what was arriving. Here is the concept I named in the opening and have not yet fully explained. There is a boundary surrounding you right now, surrounding Earth, surrounding this galaxy, surrounding everything that has ever been observed or measured or detected by any instrument ever built. It has a name, though astronomers rarely say it in ordinary conversation. It is called the particle horizon. It marks the edge of the observable universe, the furthest distance from which light has had time to reach us since the Big Bang, 13.8 billion years ago. Everything within that boundary we can, in principle, observe. Everything beyond it lies outside our causal past. Its light has not had time to reach us. It may be nearly identical to what surrounds us. It may differ in ways we cannot anticipate. We have no way to determine which is true, and the physics of an expanding universe ensures we never will. But the particle horizon contains something more unsettling than its outer edge. Every object within the observable universe is visible to us, not as it is, but as it was. The most distant galaxies we can detect are visible as they were roughly 13 billion years ago, in the universe's early period, when galaxies were young and chaotic, and bore little resemblance to what they became. We are seeing the infancy of structures that have since matured, collided, transformed, or in some cases ceased to exist in any recognizable form. The observable universe is not a photograph. It is a composite image assembled from light that left its sources at vastly different moments in history, all arriving simultaneously, all displayed in the same frame. When you look at a single image of the night sky, the nearest star may be 4 light years old. The furthest galaxy may be 12 billion years old. They appear in the same image as if they were contemporaries. They are separated by an interval of time longer than the current age of the Earth. The sky is a fiction of simultaneity. Consider what this means for the concept of location. When astronomers say a galaxy is 10 billion light years away, they mean something specific. The light we receive from it now left its source 10 billion years ago. That is where the galaxy was 10 billion years ago. Where is it now? In those 10 billion years, the universe has continued to expand. The galaxy has moved. Its stars have aged. Some have died. New ones may have formed. The galactic structure may have merged with neighbors, been disrupted, transformed beyond any resemblance to the image in our telescopes. What we are looking at does not exist. Not in the form we are seeing it, possibly not at all. Every observation of the distant universe is an observation of something that is already gone. This is not a problem that patience or technology will correct. It is the permanent condition of any observer in a universe where information travels at a finite speed and space itself is expanding. Any civilization that has ever existed or ever will exist, regardless of its sophistication, faces this same boundary. You cannot see the universe as it is. You can only see it as it was. And yet, you can see it. That is the part that requires a moment. For 13 billion years, the universe was transmitting. Galaxies were emitting light that traveled across expanding space, through the early universe, through the formation of the Milky Way, through the emergence of the solar system, through the entire history of life on this planet, and it was transmitting to no one. There were no instruments, there were no observers. The light arrived at empty space or ocean or rock and passed through unreceived. And then, in the last fraction of the universe's current age, a species built the instruments to receive it. We became the first arrangement of matter, as far as any evidence suggests, capable of understanding what that arriving light contained and what it said about the distance it had traveled and therefore about the time it represented. Liggett in her chair, measuring the periods of variable stars on photographic glass. Rømer before the Academy, predicting a 10-minute delay no one believed was possible. These are not dramatic acts. They are precise, patient, careful ones, conducted in rooms with insufficient resources by people whose contributions were underestimated by the institutions that employed them. Through those acts, we learn to read the light. Return now to Paris. November 9th, 1676. The eclipse of Io arrives 10 minutes late. In that moment, Rømer had measured the speed of light to within about 25% of its actual value, a remarkable precision given the instruments available to him. What he had determined was that light traveled at a finite speed. It was not instantaneous. It covered distance. It took time. He was thinking about the delay in terms of minutes. Jupiter to Earth. A comprehensible interval. He had no framework for what that measurement implied at the scale of galaxies or at the scale of the universe as a whole, because no one in 1676 could have possessed such a framework. The tools to see that far did not exist. The concept of other galaxies did not exist. Even the true distance to the nearest star was unknown. In the 3.5 centuries since that evening in Paris, we have extended Rømer's observation outward in every direction. We have measured the speed of light with extraordinary precision. We have calculated the age of the universe. We have built instruments capable of detecting photons that have been traveling for nearly 14 billion years. Photons carrying information about the state of the universe when it was less than 1 billion years old. And what we have found, at every scale, is the same thing Rømer measured from the eclipse of a moon. Light travels. It takes time. The universe does not reveal itself instantaneously. The difference is only one of magnitude. Rømer's 10-minute delay has become 13.8 billion years. His measurement of a single moon's eclipse has become the edge of the observable universe. His simple, demonstrable, once disputed fact, light is not instantaneous, has extended into a constraint on all possible knowledge, for all possible observers, everywhere, at any moment. Every telescope ever built is a time machine. Not in metaphor. The further it sees, the further back it reaches. The most powerful instrument that will ever be constructed will show us the universe, not as it is, but as it was earlier and earlier in its history, approaching but never reaching the moment of the Big Bang itself, the one event from which no light has yet had time to arrive. We live inside a sphere of the past. The sphere is expanding. Each second, new light arrives from distances that were previously beyond reach, carrying images of events that occurred billions of years ago, and only now complete their journey to our instruments. The universe is sending us its history continuously, generously, at the only speed the physics permits. And here is what gives that transmission its weight. Io is still orbiting Jupiter. Tonight, somewhere along the path of a telescope, its shadow is crossing the Jovian surface, and an eclipse is beginning. The light from that eclipse will take 40 minutes, or 60, or 80, depending on where Earth and Jupiter stand in their orbits, to reach us. By the time it arrives, the eclipse will be over. Io will have moved on. That specific arrangement, that exact position of a small moon relative to a giant planet, will be gone. And we will be seeing it for the first time. This is how every observation works. This is how it has always worked. Every photon that reaches your eye carries a past. It has already left behind. Every star in the sky is a transmission from a moment that no longer exists. Every galaxy in every photograph is a record of something that has already changed. The sky is not the present. It is everything that was arriving continuously, patiently, at the only speed the universe allows. Rømer measured a 10-minute delay and became the first to understand, with evidence, that the universe withholds its present from us. What he could not have known standing in that room in Paris is that this withholding is not a flaw in the physics. It is the physics. And the fact that a species arose on a small planet around an ordinary star and built the instruments to understand what the delay means and trace that 10-minute interval outward across billions of light years of time, that is not something the universe arranged. It is something that happened inside it. You are not a witness to the cosmos. You are its memory.